Good evening, Professor. This is my submission for Lab 4 of Com 380 course. So, first of all, in local search, how do we determine neighbors? Neighbors refers to states which are in direct reach of current state and can be obtained by making a single modification. There are three types of basic local search algorithms, and we determine neighbors in all of them differently. First one is the greedy descent, which is highly based on exploitation. In this, we determine the best neighbor by solely focusing on exploitation, and we analyze the most optimum neighbor and go to that neighbor, uh, which makes this algorithm a little bit faster and faster, but it does have the danger of getting stuck in local optima. The second one is randomized local search. This is a heavily exploration based algorithm in which we randomly allocate neighbors so that we can cover the whole solution state. This kind of algorithms are better if the solution state has lot of local maximas and the our algorithms have can get stuck. The second one is the combination of exploration and exploitation. This is something like simulated annealing or greedy descent with random initialization. In these kind of algorithms, we determine the neighbors by combination of exploration and exploitation, so we don't get stuck in local optima and we can find global optima. These are the best kind of algorithms. The only difficulty is that it is difficult to implement them. What is the difference between random walk and random reset? Random walk is just you move randomly through the solution space until the solution is found, and random reset, the only thing which is random is the initialization. The search algorithm can be random or not random. What are the two weaknesses of scholastic search? The first one is that it is not guaranteed to find the best global solution. It can get stagnant, as I mentioned above. And the second one is that it cannot guarantee that there is no solution. That means it cannot prove it. Question D. Given all the information above, which variable will be selected? Although there are different variants of greedy descent, but based on the information above, we which is that we will carry this descent in two stages: selecting the variable most conflict and assigning the value with to the value that the variable that minimizes the conflict. So that will be will be selecting intersection one and will be assigning stop sign to it. And the final question is that in the partial CSP figure given to us, would we likely to find a solution within 100 steps? So as you can see, based on my research, using thousand random walks with the limit of 1,000 steps, you can see I only came out to be 100 steps only one time. The mean is near 12 steps, and it gives us 90% probability that we'll find the solution within 30 steps. So based on that information, I can say it is very probable that you can find a solution within 100 steps. I can run this problem too, as I've ran it here. You can see for the second time, this time the max was 106, but the 90 percentile is 32. If we run it again, as you can see, this time the max was 101 and the 90th percentile is 34 steps with mean of some 13. So most likely than not, it will find it within 100 steps. These are the options, but this doesn't mean this is the most optimal solution. Probably the most optimal solution will be something like greedy descent with random resets. Let's see. Okay,